Okay, so in the last lecture, we have seen about the convolution theorem, and then we have solved the problems based on convolution theorem. So let us try some more examples based on the convolution theorem. Yeah. So we have seen the convolution theorem. So in short, I'll revise it. So what we have is, suppose let Laplace inverse of f1 bar of s is equal to f1 of t, and Laplace inverse of f2 bar of s is equal to f2 of t. Okay, then we have Laplace inverse of f1 bar of s into f2 bar of s, and that's equal to integral 0 to t f1 of u into find inverse Laplace transform of f bar of s is equal to s upon s square plus a square s square plus b square. So that's what we have. Okay, so we'll try this problem. Okay, now using convolution theorem. Okay, so we go with the solution. Let what we have, f bar of s is equal to s upon s square plus a square s square plus b square. So first step we have to consider s upon, or either we consider 1 upon, okay, so 1 upon s square plus a square s upon s square plus b square. So we get here f bar of s is equal to 1 upon s square plus a square, and this is s upon s square plus b square. Okay, so that's what we have. Now the first step we have completed. So we will go for the second step. So we have Laplace inverse of 1 upon s square plus a square. This is equal to sine of at upon a. Let this be f1 of t. Laplace inverse of s upon s square plus a square. This is equal to cos of at Let this will be f2 of t. And now we apply the convolution theorem. So by convolution theorem, we have, so Laplace inverse of f bar of s is equal to, we have integral 0 to t f1 of u into f2 of t minus u du. Okay, so this is equal to integral 0 to t 1 by a. This is going to be sine of au into cos of at minus au du. Okay, um, so we have to be careful. So that's what we have. It's going to be b square, and this time may be cos of bt. Okay, so I hope that's correct now. Yeah. Okay, so this will be bt minus bu. So we got this 1 by a 0 to t sine of au into cos of bt minus bu. So we can use the formula 0 to t. What is the formula for this? We may have, okay, so we have the term sine into cosine. So we have sine a into cos b is equal to half of sine a plus b plus sine a minus b. So this is what we have. So using this, we are able to write half of sine of au plus bt minus bu plus sine of au minus bt plus bu, and this is du. So we can simplify this as 1 by 2a integral 0 to t. We get here sine of a minus b into u plus bt plus sine of a plus b into u minus bt, and this is du. Okay, so this is equal to 1 by 2a. Now we can have this integral. Okay, so we have sine term, and hence the integral of sine term we are able to write as, so what is the formula? Integral of sine of ax plus b dx is equal to minus cos of ax plus b upon a. So using this formula, we are able to get here that this will be minus cos of a minus b into u plus bt upon a minus b minus cos of a plus bu minus bt upon a plus b, and the limits are 0 to t. Okay, so 1 by 2a. Now apply the limit. So if I try to apply the limit for this, then what I'll have is minus cos of. So if I put t, then I'll get a t minus bt plus bt upon a minus b. Now we'll have this term. So I'll be having cos of so this will be a plus at. So what I'll get here? This will be at plus bt minus bt upon we'll get a plus b. Now what is the next term we have here? So if we put 0, what I'll get is this will become plus. Okay, so we get plus here because we are using lower limit, minus minus plus. Then we have this will be cos of this u will be 0. Now this term will be bt upon we have a minus b minus this will become plus now. So cos of minus bt upon a plus b. Okay, so that's what we'll be having the term. Okay, and now since we know cos of minus theta is equal to cos of theta, so this is equal to 1 by 2a. Then this is the term minus cos of at upon a minus b minus cos of at, and this will be a plus b plus cos of bt upon a minus b and plus cos of bt upon a plus b. Okay, so we can simplify this as 1 upon 2a. In this minus cos of at we can have common, and we'll be having the term here 1 upon a minus b minus 1 upon a plus b plus cos of bt common 1 upon a minus b. This term will be plus 1 upon a plus b. Now we have this is 1 upon 2a, and we can see this term is common. So I'll be having 1 upon a minus b plus 1 upon a plus b, and here we'll get cos of bt minus cos of at. Now let us simplify this. Okay, so we have 1 by 2a. By cross multiplication, we'll having a plus b plus a minus b upon a square minus b square. And this is cos of bt minus cos of at. So this is equal to 1 by 2a, and we get here 2a upon a square minus b square. Okay, now this term is as it is cos of bt minus cos of at. Okay, and now this 2a will get cancelled, so we get 1 upon a square minus b square cos of bt minus cos of at. So this is what we have obtained, Laplace inverse of f bar of s. So we get here that hence Laplace inverse of s upon s square plus a square into s square plus b square is equal to 1 upon a square minus b square, and here we got cos of bt minus cos of at. So This is what we are able to get the terms. Okay. So here we got this problem by using the convolution theorem. Okay. Now, do you have any problem in this question or any doubt in this question? I hope all of you have marked your attendance. So please mark your attendance. Okay, that is mandatory. And please write your name and surname. Okay, so some people are just writing name or some people are just writing surname. So please write your name and surname, and your attendance later after 11:30 will not be considered. No problem. So you have the time till 11:30. You have to mark your attendance. Okay. Okay. So we'll see now how to use the derivative to find the Laplace inverse. Okay. So let us see the another formula to find the inverse Laplace transform. Okay. So we'll go with the use of derivative for inverse Laplace transform. As use of derivative. Okay. Now, when we have to use this property. Okay. So this property is particularly used for the functions like log, tan inverse. Then we have for cot inverse. Then we have for cot inverse, and then we have for hyperbolic tan inverse. So we know that in first semester that hyperbolic tan inverse can be expressed as a log. So hyperbolic tan inverse of z is equal to half of log of 1 minus z upon 1 plus z, so that we can express this as a log. So basically we have these three functions where we have to use this property. Okay. So let us try the example based on this. So we consider find inverse Laplace transform of f bar of s is equal to log of s plus b upon s plus a. So we have to find the inverse Laplace transform of this. You can see this is exactly the log term that we want, and so here this property should be used. Okay. So we'll go with the solution late. Okay, f bar of s is equal to. So what we have here, this is going to be log of s plus b upon s plus a. Okay, now we need to understand how to use this property. So this property we should use in three steps. Okay, what are the three steps? So first, find the derivative of given function. Second, find its inverse, so inverse of the derivative. And third step, multiply the inverse by minus 1 upon t. So these are the three steps that we have to follow to find the inverse Laplace transform in this case. Now we'll follow these three steps for our example. Okay, so the first step is to find the derivative, but I'll tell you that don't be in hurry. So if you want to find out the derivative of this term, it's easy. So what will be the derivative? The log of the derivative of log is going to be 1 upon this term, and then again the derivative of this term, so which will be u upon v rule. It will be more complicated. We can find it, but it will take more time and more complicated. So how easily we are able to do that? What we know is log of a by b is equal to log of a minus we have log of b, and hence we can write this as this will be log of s plus b minus log of s plus a, and this is your f bar of s. Now see, taking the derivative of this term, and then again we have to go to partial fraction and taking the derivative of this term, which you find more easy. So finding the derivative of this term is more easy than finding the derivative of this term. And that's why, as I said, don't be in hurry. So we have derivative of f bar of s is equal to d by ds of log of s plus b minus log of s plus a. And this will be 1 upon s plus b minus 1 upon s plus a. So easily we got the derivative d by ds of f bar of s. And now consider inverse Laplace transform of this derivative. Okay, so d by ds of f bar of s is equal to Laplace inverse of 1 upon s plus b minus s 1 upon s plus a, and using the linearity property we have Laplace inverse of s plus b minus Laplace inverse of 1 upon s plus a. Now we find the inverse. So this is e raised to minus bt minus e raised to minus at. So we got the Laplace inverse of d by ds of f bar of s. So here we have completed the second step. Now we have to think of the third step. So we have Laplace inverse of f bar of s is equal to minus 1 by t Laplace inverse of d by ds of f bar of s. So this is minus 1 by t, and this already we have calculated e raised to minus bt e raised to minus at. Okay, and now this is equal to, so what we get, e raised to minus at minus e raised to minus bt upon t. So we got Laplace inverse of inverse of f bar of s, and hence what we get here, Laplace inverse of log of s plus b upon s plus a is equal to e raised to minus bt e raised to minus at upon t. Okay, so that's how we are able to get the inverse Laplace transform using the property that use of derivative. Okay, so here what are the important steps that we have considered? The first step was to find the derivative. Okay, after finding the derivative, the second step was to find the inverse Laplace transform of this derivative. Okay, and after finding the inverse Laplace of this derivative, the third step is to use the property. Okay, so this way, by using these three steps, we were able to get the inverse Laplace transform of this given function. So is there any doubt in this property and in this example? Okay, that's good. That's great. Okay, so no problem. Then we'll go for one more example based on this. Okay, so let us see the another example. Now we have find inverse Laplace transform of f bar of s is equal to log of root of s square plus s square upon s. So that's what we have. So we go with the solution. Let f bar of s is equal to log of root of s square plus a square upon s. So as I said, don't be in hurry. First simplify this function and then better find the derivative. So log of root of s square plus a square minus log s. So this is log of s square plus a square raised to half minus log s, or this is half of log of s square plus a square minus log s. Okay, so this is f bar of s. So first try to understand the function. What is the given function? Try to get its simplest form and then apply the derivative. So now we have the simplest form of this f bar of s, and so we are able to apply the derivative. So I'll consider d by ds of f bar of s, and that is equal to d by ds of half of log of s square plus a square minus log of s. So this is half of d by ds of log of s square plus a square minus d by ds of log of s. So this is equal to half of the derivative of log is going to be 1 upon s square plus a square, but the derivative of this term will be 2s, and minus the derivative of log x is 1 by x, so it is going to be 1 by s here. This 2 and this 2 will get cancelled. So once you cancel this 2 and this 2 in the denominator, what you'll get is s upon s square plus a square minus 1 by s, and this is d by ds of f bar of s. So here we have completed the first step. Okay, so as we have completed the first step, we have to consider the inverse Laplace transform of this derivative. Now we have inverse Laplace transform of d by ds of f bar of s is equal to Laplace inverse of s upon s square plus a square minus 1 upon s. So this is Laplace inverse of s upon s square plus a square minus Laplace inverse of 1 by s. Okay, and now we get this is going to be cos of 80 minus 1. So we got here the inverse Laplace transform of d by ds of f bar of s. So now this completes our second step. So we have to consider the formula, and hence now we have inverse Laplace transform of f bar of s is equal to minus 1 by t Laplace inverse of d by ds of f bar of s. So this is minus 1 by t, and this inverse already we have calculated. So it is cos of 80 minus 1, or we can simplify this as 1 minus cos of 80 by t. So here we get the inverse Laplace transform of f bar of s is equal to 1 minus cos of 80 by t, and hence we have Laplace inverse of log of root of s square plus a square upon s is equal to 1 minus cos of 80 upon t. So that's what we can have the Laplace inverse transform for this function. So again, we need to understand that how we used the 3 steps to calculate the inverse Laplace transform. Now, do you have any doubt or any question in this example? No doubt. Okay, that's good. Okay, that's great. Okay, no problem. So we'll try one more example based on this. So let us try the another example. So we'll go with find inverse Laplace transform of log of s square plus b square upon s square plus a square. So we'll go with the solution. Let f bar of s is equal to log of s square plus b square upon s square plus a square. And then we can write this as log of s square plus b square minus log of s square plus a square. So this is f bar of s. Then we consider the derivative f bar of s. So we have d by ds of log of s square plus b square minus log of s square plus a square. Now this is d by ds of log of s square plus b square minus d by ds log of s square plus a square. So let us find this derivatives. This is equal to 1 upon s square plus b square into 2s minus 1 upon s square plus a square into 2s. The derivative of log is going to be 1 by the term, and the derivative of this term is going to be 2s. So here we can write as 2s s square plus b square minus 2s s square plus a square, and this is d by ds of f bar of s. Okay, so now what we get here, we got the second step completed. First step completed, we got the derivatives. Now we'll find the inverse Laplace transform of this. So we have inverse Laplace transform of d by ds f bar of s. So this is inverse Laplace transform of d by ds f bar of s. So minus twice cos of 80. So that's what we get here. Now what we have, Laplace inverse of d by ds of f bar of s. And this completes our second step. So now let us calculate using formula. So now consider Laplace inverse of f bar of s is equal to minus 1 by t Laplace inverse of d by ds f bar of s. So we got this minus 1 by t. Then here we have twice cos of bt minus twice cos of at. So we can simplify this as twice cos of at minus cos of bt upon t. So this way we are able to get inverse Laplace transform of f bar of s is equal to twice cos of at minus cos of bt upon t. And hence we got inverse Laplace transform of log of s square plus b square upon s square plus a square, and this is equal to twice cos of at minus cos of bt upon t. So this is how we are able to get the inverse Laplace transform of the function using the property of derivative, use of derivative. So do you have any doubt in this example or any problem? Using the property of derivative. Now, in this property, the first step is to find the derivative of the given function. The second step is to find the inverse of the derivative of the function. And the third step is use the property of derivative. So how do we use the property of derivative? So the Laplace inverse of f bar of s is equal to minus 1 by t into Laplace inverse of the derivative of f bar of s. So this is how we are able to use this property. Okay, let's have one more example. Okay, so we'll go with one more example. Okay, we can have find inverse Laplace transform of tan inverse of 2 by s. Okay, so this is what we have. Okay, we go with the solution. Let f bar of s is equal to tan inverse of 2 by s. Okay, so we have to be careful. We want to find out the inverse of this. So if I want to find out the inverse, first step I want to find out the derivative of tan inverse. Okay, so what is the derivative? D by dx of tan inverse x is equal to 1 upon 1 plus x square. Here we need to be careful that yes, this is the correct formula, but when we have only x, if you have f of x, so tan inverse of f of x, then we have to be careful that 1 plus f of x bracket square into d by dx of f of x. So this is the formula that we have to use here. And most of the student here commit mistake that they do not find that this derivative, and that's why their answer will go wrong. So please be careful. Okay, so now consider the derivative d by ds of f bar of s is equal to t by ds of tan inverse of 2 by s. Okay, and what is derivative we have? So this is equal to 1 upon 1 plus 2 by s square, 2 by s and bracket square into d by ds of 2 by s. Okay, so this is equal to 1 upon 1 plus 2 by s bracket square into this 2 remains as it is. The derivative of 1 upon s is 1 by s square. Okay, so this is equal to 1 upon 1 plus 4 by s square, and this term is minus 2 by s square. So this s square we can take in the numerator, and then we can have this as this is equal to, see, we'll have s square upon s square plus 4, and here we have this minus 2 upon s square. So this s square and this s square will get cancelled. So we'll be having minus 2 upon s square plus 4. So we got d by ds of f bar of s is equal to minus 2 upon s square plus 4. So this is our first step. Now we have Laplace inverse of d by ds of f bar of s is equal to Laplace inverse of minus 2 upon s square plus 4. And this is minus 2 Laplace inverse of 1 upon s square plus 4. So this is equal to minus 2 sine of 2t by 2. Okay, so that's what we are able to get. And hence we get Laplace inverse of d by ds of f bar of s is equal to minus sine of 2t. This 2 and this 2 will get cancelled. Okay, now we consider the formula use of derivative. So Laplace inverse of f bar of s is equal to minus 1 by t, and Laplace inverse of d by ds f bar of s. So this already we have calculated. So minus 1 by t minus sine of 2t, and hence we are able to write this as Laplace inverse of f bar of s is equal to sine of 2t by t. So we got here Laplace inverse of tan inverse of 2 by s is equal to sine of 2t by t. So this is how we are able to get the inverse Laplace transform by using the property use of derivative. So do you have any doubt or any question in this example, or up to 8? Okay, that's great. You don't have any doubt. Good.